What China is building right now will leave you speechless. You're about to witness 10 engineering projects so massive, so complex, and so audacious that they're rewriting the rules of what's physically possible on this planet. We're talking about structures that move entire rivers across continents, bridges that float above clouds, and ports run entirely by machines. These aren't proposals or dreams, they're standing right now, and the engineering behind them will blow your mind. But here's what makes China's Three Gorges Dam truly unfathomable. It required pouring enough concrete to build 45 Hoover dams. You heard that right, 45 Hoover dams worth of concrete for a single structure. And that's just the beginning of what you're about to discover. Three Gorges Dam. You're standing before a wall that required removing over 102 million cubic meters of earth, enough dirt to bury Manhattan under 100 feet. The Three Gorges Dam isn't just China's largest construction project. It's a concrete fortress that demanded engineers solve problems no one had ever faced before. Here's where it gets insane. The construction teams needed to dump 400,000 cubic meters of concrete every single month for years without stopping. Engineers built two massive aggregate processing systems that could churn out 2,380 cubic meters of concrete per hour, with each batch cooled to exactly 7 degrees Celsius in summer to prevent cracking. The concrete had to be that cold because when it cures, it generates heat, and in a structure this massive, that heat could cause catastrophic fractures. But the real engineering nightmare was the Yangtze River itself. You can't just stop one of the world's most powerful rivers and start building. Engineers built cofferdams to hold back a river, pushing 83,700 cubic meters of water per second. That's like holding back 33 Olympic swimming pools worth of water rushing at you. Every single second, one miscalculation during demolition could have destroyed the entire power plant. Then came the turbines. Each of the 32 main turbines generates 700 megawatts of power, making them the largest ever built when installed. These precision instruments the size of houses faced an unexpected threat: microscopic bubbles eroding the guide vanes through cavitation, tearing metal apart with explosive force. The dam wall itself stands 607 feet tall and 1.45 miles long. Built with 27.2 million cubic meters of concrete reinforced, with 463,000 tons of steel. But China wasn't done pushing boundaries on a bridge that doesn't just cross a valley, it floats above the clouds. Duge Bridge. You think you know what a high bridge looks like until you meet the Duge Bridge. You are driving on a road in the sky, hanging more than half the height of the Empire State Building above a raging river, with nothing but engineered steel and concrete between you and the abyss. Under your wheels is not just a highway. It is a structure that forced engineers to rethink how you even build anything when the ground beneath you is almost impossible to reach. From the first design sketches, the problem was brutal. You have two cliffs, a deep gorge, and almost no access from below. You cannot just roll in cranes and scaffolding like a normal highway job. So engineers designed a steel truss deck stretched between mountain anchors, with pylons planted directly into hard rock that had to be drilled, blasted, and reinforced from narrow platforms barely wide enough for equipment. Every foundation location had to be positioned with surgical precision, because if those anchors were off by even a few inches, the entire deck alignment and load path would be compromised. Then came the part that would make your palms sweat: pulling the first lines across the gorge. Helicopters carried slender pilot cables over the canyon, weaving the first fragile threads of what would become massive load-bearing systems. In shifting mountain winds that could twist steel and swing loads like wrecking balls, crews working at terrifying heights had to clamp, tension, and adjust each segment so the finished bridge would settle into its exact design profile. Up there, one mistake did not just risk a life, it could torque the entire structure out of shape. When the final deck sections launched from each side finally met and locked together high above the river, it was not just another bridge opening. It was proof that China could literally draw a line through thin air and then turn it into a highway you can actually drive on. But this was just the beginning, because the next project does not just hover over the water, it slices across the ocean and dives underneath it, linking three major cities in one continuous engineered gamble: Kong-Zhuhai-Macau Bridge. You're looking at 34 miles of bridge and tunnel stitched across open ocean, connecting 3 cities that were once separated by hours of travel. The Kong-Zhuhai-Macau Bridge doesn't just span water, it disappears beneath it, threading through one of the planet's busiest shipping lanes without blocking a single cargo vessel. And the engineering required to pull that off is nothing short of terrifying. Here's the nightmare. You need to keep massive container ships moving overhead while simultaneously building a tunnel on the sea floor below. Engineers couldn't drill a tunnel through bedrock like a normal subway. The seabed was too soft and unstable, so they built the tunnel in sections. 33 prefabricated tubes, each weighing 80,000 tons, constructed on shore and then floated out to sea. Picture lowering a building, the weight of 50 statues of liberty, onto the ocean floor with millimeter precision, then doing it 32 more times in perfect alignment. One miscalculation in currents, one shift in positioning, and the tunnel sections wouldn't seal, leaving gaps that would flood the entire structure. But that's not even the hardest part. To connect the bridge sections to the underwater tunnel, engineers had to construct 2 artificial islands in the middle of the open ocean. They dropped massive steel cylinders into the seabed, then pumped out the water and filled them with sand and rock to create stable platforms. These islands had to withstand typhoons packing winds over 120 miles per hour while supporting bridge ramps, ventilation systems, and tunnel portals, all built on ground that didn't exist 3 years earlier. The bridge deck itself had to flex and move with thermal expansion across miles of steel and concrete, accommodating shifts that could throw off alignment by feet if the joints weren't engineered to slide and adjust. But even this feat of ocean engineering pales compared to what China pulled off on an island that shouldn't exist at all. Flower Island. You're standing on land that was pulled from the ocean floor, grain by grain, until an entire island materialized where there was nothing but open water. Flower Island isn't a natural formation. It's a constructed landmass that required engineers to literally build the ground beneath their feet before they could build anything on top of it. And the process of creating solid earth in the middle of the sea is far more violent than you'd imagine. The first challenge was brutal. You can't just dump sand into the ocean and call it an island. The currents would wash it away in hours. Engineers had to construct a massive perimeter containment system, driving sheet piling deep into the seabed to create a watertight barrier that could hold millions of cubic meters of fill material. These weren't small stakes. They were interlocking steel walls, driven dozens of feet down, fighting against water pressure and unstable sediment that wanted to collapse inward with every wave. Then came the fill operation. And this is where the scale becomes incomprehensible. Dredging vessels working around the clock sucked sand and sediment from approved offshore zones, then pumped it through pipelines into the contained area. Layer after layer, the island rose from beneath the surface, with each new elevation requiring compaction so intense it could turn loose sand into weight-bearing ground. Engineers used dynamic compaction, dropping massive weights from cranes repeatedly to compress the fill, because if the ground wasn't solid enough, every building would eventually sink or tilt. But creating stable land was only half the battle. The island's infrastructure had to be designed to handle the unique soil composition, with foundation systems that distribute loads across wider areas than normal construction would require. This wasn't just an island, it was an engineering proof of concept that China could manufacture territory itself. And if you think building land is ambitious, wait until you see what they built underneath a river that's been flooding cities for thousands of years. Jinan-Huanggang Road Yellow River Tunnel. You're about to drive under a river that's been called China's sorrow for how many times it's changed course and drowned entire regions. The Jinan-Huanggang Road Yellow River Tunnel doesn't just go beneath water, it burrows through some of the most treacherous soil conditions on Earth, where the ground shifts like liquid and every excavation risks catastrophic flooding. And the machines cutting through this nightmare had to be engineered specifically for conditions that would destroy normal tunneling equipment. The problem was immediate. The Yellow River sits on top of sediment deposits so soft and waterlogged that digging through them is like trying to tunnel through wet concrete that wants to collapse inward with crushing force. Standard drill and blast methods would trigger immediate flooding. So engineers deployed tunnel boring machines, massive cylindrical beasts with rotating cutting heads that chew through soil, while simultaneously installing concrete liner segments behind them. These aren't just big drills, they're mobile factories weighing thousands of tons, pushing forward while maintaining air pressure inside the tunnel that's higher than the water pressure outside, creating a barrier that keeps the river from pouring in. But here's where it gets insane. The tunnel had to be built as a dual-tube system, one for vehicles and one for metro trains, running side by side beneath a riverbed that's constantly shifting. The boring machines had to stay level and aligned to within millimeters across miles of excavation, because if the tubes deviated even slightly, the connecting passages and emergency exits wouldn't line up. Laser guidance systems track position in real time, adjusting the cutting head angle with hydraulic jacks that could compensate for soil resistance, pushing the machine off course. The liner segment's massive curved concrete panels had to seal perfectly against water pressure that could shoot jets through any gap with enough force to cut steel. But that engineering precision under a deadly river is nothing compared to what China built on the surface in a city where the ground itself is a vertical maze. Chongqing East Railway Station. You're about to step into a railway station built on a city that exists in 3 dimensions. Chongqing doesn't sprawl across flat land, it climbs mountains, and the East Railway Station had to be engineered into terrain so steep that the platforms, waiting halls, and transit connections stack on top of each other like a vertical puzzle. This isn't just a big building, it's a gravity-defying transportation hub that required engineers to anchor massive structures into slopes that wanted to slide downhill. The foundation work was a nightmare from day one. You can't just pour concrete footings on a mountainside and expect them to hold up a station designed to handle hundreds of thousands of passengers daily. Engineers drove deep pilings into bedrock, some extending over 100 feet down through loose soil and fractured rock layers until they hit solid stone that could bear the load. Each piling had to be positioned with laser precision because the entire station structure distributes weight across these underground anchors. If even a few were misaligned, the building could settle unevenly and crack apart. Then came the real engineering challenge, creating level platforms on land that naturally slopes at angles that would make you dizzy. The station is built in multiple tiers, with some sections cantilevered out over empty space, supported by massive steel trusses that transfer loads back to the mountain face. The roof structure alone spans enormous distances without interior columns blocking passenger flow, requiring pre-stressed concrete beams and steel frameworks engineered to flex slightly under wind and thermal loads without compromising structural integrity. But the most insane part is the integration roads, metro lines, and pedestrian bridges all converge at different elevations, threading through the station at levels that required excavating into the mountain while simultaneously building upward. Every connection point had to align perfectly, despite being designed by different engineering teams working on structures that wouldn't be completed for years. Yet even this vertical engineering marvel is dwarfed by what China built where the ocean meets the machines. Yangshan Deepwater Port. You're watching containers move themselves. Yangshan Deepwater Port isn't just built on islands 30 kilometers offshore. It's a fully automated facility where machines orchestrate a ballet of steel boxes without a single human touching the controls. And the engineering required to make robots run an entire port in the middle of the ocean is beyond anything you've seen before. The first problem was location. Deepwater ports need depth that most coastlines can't provide, so engineers built this one on islands connected by the Duge Bridge, a 20-mile ocean crossing that had to withstand typhoons while carrying thousands of trucks daily. But the islands themselves weren't large enough, so they were expanded using land reclamation, dumping millions of tons of rock and fill to create artificial berths where container ships longer than aircraft carriers could dock. Then came the automation, and this is where the engineering becomes surgical. Automated guided vehicles navigate the port using magnetic tracks embedded in the pavement, each one carrying containers weighing up to 60 tons, with positioning accuracy measured in centimeters. These aren't simple robots, they're synchronized with overhead cranes that lift containers off ships and place them onto the vehicles in continuous motion, communicating through networks that process thousands of movements per hour, without collision or error. The cranes themselves are engineering monsters. Each automated gantry crane spans the width of a megaship, using laser sensors and cameras to identify container positions, then grip and lift them with precision that human operators couldn't match in speed or consistency. The control systems had to account for wind loads, ship movement from waves, and the flex of the crane structure itself, all calculated in real time to prevent a 60-ton container from swinging loose. But if you think moving containers with machines is impressive, wait until you see what China did to move something far more precious and far more dangerous to get wrong. South-North Water Transfer Project. You're looking at the most ambitious water diversion project ever attempted. A system designed to move 44.8 billion cubic meters of water every year from southern China to the parched north. The South-North Water Transfer Project isn't a single canal. It's 3 separate routes spanning thousands of miles, each one requiring engineering solutions that push the limits of what's possible when you're trying to make water flow uphill. The central route is where the engineering becomes almost unbelievable. Water has to travel over 700 miles and climb in elevation, which means you can't just dig a ditch and let gravity do the work. Engineers built massive pumping stations capable of lifting millions of gallons per hour, with motors so powerful they required dedicated electrical substations just to run them. The canals themselves had to be lined with concrete to prevent seepage, because losing even a fraction of the water to absorption across that distance would make the entire project economically worthless. But the real nightmare was crossing obstacles. The route cuts through hundreds of rivers, roads, and railways that couldn't be shut down during construction. So engineers designed inverted siphons, massive underwater pipes that drop the canal beneath existing waterways, then bring it back up on the other side. Each siphon required precise hydraulic calculations, because if the flow rate or pressure drops weren't perfectly balanced, the entire system could back up or create water hammer effects powerful enough to burst the pipes. Then there's the tunnel sections, where the canal burrows through mountains too large to go around. Boring these passages required tunnel boring machines working in conditions where hitting an unexpected aquifer could flood the entire excavation in minutes. The alignment had to maintain exact gradients across miles of underground construction too steep, and the water velocity would erode the tunnel walls. Too shallow, and the flow would stagnate. And if you think moving water across a continent is extreme, the next project moves people faster than physics should allow. China Maglev. You're about to float above the ground at speeds that make conventional trains look like they're standing still. China's Maglev system doesn't use wheels. It uses magnetic levitation to suspend the entire train in midair, eliminating friction and unlocking velocities that wheeled vehicles simply cannot reach. And the engineering required to make tons of steel hover with millimeter precision while screaming through tunnels at over 300 miles per hour is almost incomprehensible. The track itself is the key to everything. Unlike normal rails, Maglev guideways are lined with powerful electromagnets positioned with surgical accuracy along the entire route. These aren't passive magnets, they're electronically controlled coils that switch polarity thousands of times per second, creating magnetic fields that both lift the train and propel it forward. If even one section falls out of alignment or loses power, the train could drop or destabilize at lethal speeds. Then came the levitation gap, the space between the train and the guideway, that has to remain constant whether the train is stationary or moving at maximum velocity. Sensors monitor this gap in real time, adjusting the magnetic field strength instantaneously to compensate for weight shifts from passengers moving inside, wind gusts pushing against the train body, or track irregularities. The control systems are processing data and making corrections faster than human reaction time, because at these speeds, even a momentary loss of levitation could be catastrophic. The guideway construction had to be absolutely rigid. Any flex or settling in the support structure would throw off the magnetic alignment, so engineers built elevated concrete beams with tolerances measured in fractions of an inch across miles of track. But even this magnetic miracle is nothing compared to the final project. An offshore platform that redefines what's possible in one of the harshest environments on Earth. Dongying HG-14 project. You've built on solid ground your whole life. You've never had to think about what's underneath you. China didn't have that luxury with the Dongying HG-14 project, and they built anyway. This project sits not on land, but in the sea. 8 kilometers off the coast of Dongying in Shandong province, in the shallow coastal waters of the Yellow Sea. Depths between 1 and 4 meters, not deep enough to feel safe, not shallow enough to feel like solid ground, just enough water to make everything 10 times harder. But the tension wasn't just in the depth. Engineers had to design a foundation system capable of surviving the open ocean waves, tides, strong winds, and something most people don't think about: seasonal sea ice. Every one of the 11,736 steel piles driven into that seabed had to be calculated to hold against forces that don't stop. Ever. Then came the real problem. This wasn't a sheltered lagoon or a reservoir. This was open sea, and the structure had to be engineered to last decades in one of the harshest marine environments on the planet: marine-grade steel. Cathodic protection systems against corrosion, platforms locked rigid against currents that never rest. What they built on that water is 2,934 solar platforms, each one 60 meters by 35 meters, covering 1,223 hectares of open sea, over 2.3 million bifacial solar panels. 1 full gigawatt of power, the world's largest offshore solar farm, fully online in December 2025. A $1.2 billion structure that generates 1.78 terawatt-hours of electricity every single year, enough to cover 60% of the entire Kenli district's power demand. And because China doesn't waste space beneath those panels, in the water between the platforms, they're farming fish, shrimp, and sea cucumbers. Solar above, life below.